Welcome to this lecture on Pandas and NumPy. We'll be introducing these two essential Python libraries, which are fundamental for data analysis and scientific computing. Think of NumPy as the foundation. It provides powerful array structures and mathematical functions. Pandas is built on top of NumPy and gives us more advanced data structures, most notably data frames, which are perfect for handling the kind of real-world tabular data you'll often encounter. Throughout this session, we'll explore how to use these libraries for cleaning, manipulating, and analyzing data. We're going to cover a wide range of topics today. We'll start with an introduction to Pandas and NumPy, then move on to loading data into Pandas. We'll discuss the first steps you should always take after loading a new data set, like checking for errors and understanding its basic structure. We'll clarify the difference between categorical and continuous data, and also between regression and classification problems. A key part of our work will be performing exploratory data analysis, or EDA. We'll look at techniques for transforming and selecting important features, and even how to create new features from existing ones. To make things practical, we'll work with some real-world data sets to see how to handle common issues like unbalanced or messy data. We'll walk through examples of regression and the k-nearest neighbors algorithm. Finally, we'll wrap up by discussing some important high-level modeling concepts like generalization, overfitting, and model complexity. So, let's talk about Pandas versus NumPy. While they're often used together, they serve different purposes and have different strengths. NumPy is really optimized for speed and memory efficiency when you're doing numerical operations on arrays where all the elements are of the same type. We call these homogeneous arrays. Pandas, however, builds on this by introducing labeled data structures like series and data frames. These can handle heterogeneous data, which means you can have columns with different data types, just like in a spreadsheet or a database table. This makes Pandas the go-to tool for most data wrangling and analysis tasks. Now, looking at our notebook, the first code cell is where we import these libraries. As is the standard convention, we import NumPy as NP and Pandas as PD. This is the first step in almost any data analysis script or notebook, and we'll be using these aliases throughout. Next, we'll see how to load data into Pandas. Pandas provides a set of flexible functions to read data from many different sources, including CSV files, Excel spreadsheets, and even SQL databases. The most common function you'll use is pd.read.csv, which, as the name suggests, reads a comma-separated values file into a data frame. After loading your data, it's always important to inspect it to make sure it was read correctly. Functions like df.head to see the first few rows and df.info to get a summary of the data frame are incredibly useful for this initial check. In the next code cell, we see a demonstration of this basic data loading process. The code uses pd.read.csv to load a file named day1.csv into a data frame called df. Immediately after, it calls df.head to display the first 5 rows, which gives us a quick preview of the data's structure and content. The cell finishes by running df.isRn.sum, which counts the number of missing or null values in each column. This is a critical first step in assessing the quality of your data. Once the data is loaded, there are a few initial checks and explorations you should always perform. This helps you understand the dataset structure and quality right from the start. This process includes examining the data types of each column, checking for any missing values or outliers, and getting some basic summary statistics. Doing this early helps you plan your data cleaning and analysis strategy. The following code cell shows a comprehensive initial exploration of our data set. First, df.shape tells us the dimensions of the data, the number of rows and columns. Then df columns toList gives us a list of all the column names. df_dtypes is used to see the data type of each column. We again check for missing values with df.isnull.sum. Finally, df, describe, include all, provides a nice statistical summary of all the columns. The rest of the cell is dedicated to visualization. It creates box plots for the numeric features to help us spot outliers and bar charts for the categorical features to show the counts of each category. It even has special logic to handle date columns, plotting them as a time series to reveal any trends. Now let's discuss the types of data you'll encounter. Features in a data set can generally be classified as either categorical or continuous. Categorical features are those that take on a limited set of distinct values, like male or female for gender, or red, blue, and green for color. These can be further divided into nominal features, where there's no natural order, and ordinal features where there is a clear order. Continuous features, on the other hand, are numeric and can take on any value within a given range, such as age, income, or temperature. Understanding this distinction is fundamental for choosing the right analysis techniques and machine learning algorithms. In the world of supervised machine learning, prediction tasks are typically categorized as either regression or classification. The goal of regression is to predict a continuous numerical value, like the price of a house or the temperature tomorrow. In contrast, the goal of classification is to predict a discrete label or category, such as determining if an email is spam or not spam. The type of task you're dealing with will determine which algorithms you can use and which metrics you'll use to evaluate your model's performance. A critical step in any data analysis project is exploratory data analysis, or EDA. This is the process of visualizing and summarizing your data to understand its main characteristics. EDA helps you uncover patterns, spot anomalies or outliers, and test initial hypotheses. Some key techniques in EDA include plotting the distribution of your variables, examining the relationships between them using tools like scatter plots and correlation heat maps, and identifying any missing values. The next code cell demonstrates some of these key EDA techniques. It starts by generating a histogram for each numeric column using df.hist, which is great for understanding their distributions. Then it uses sns.pairplot from the Seaborn library to create scatter plots for every pair of numeric variables. This is a fantastic way to visualize the relationships between features. Finally, it generates a heat map of the correlation matrix with sns heatmapdf.core. This visualizes the correlation coefficients between all numeric variables, making it easy to spot features that are highly correlated with each other. Often you'll need to transform your data to make it more suitable for modeling. This is a crucial pre-processing step known as feature transformation. Common transformations include converting categorical features into a numerical format, scaling numerical features to a standard range, and creating entirely new features from existing ones, which is a process called feature engineering. In this code cell, we see an example of converting a categorical feature to a numerical one. It demonstrates a technique called label encoding. Specifically, it takes the gender column, which contains text values like male and female, and maps them to numerical values 0 and 1. This is a straightforward way to handle a binary categorical variable, making it understandable for a machine learning model. The code also visualizes the distribution of the gender column both before and after the encoding, which is a good way to verify that the transformation was applied correctly. Of course, a deep understanding of your dataset is vital for any meaningful analysis. This goes beyond just running functions. It involves checking for things like duplicate rows, identifying potential outliers, and looking for any inconsistencies in the data, such as a negative value in an age column. It's also important to understand the context and meaning of each feature. If you have a data dictionary which describes each column, you should definitely consult it. The target column, which is the variable you're trying to predict, requires special attention. It's important to analyze its properties carefully. If you're working on a classification problem, you need to check the distribution of the classes to see if the data set is balanced. If it's a regression problem, you should look at the distribution of the target to check for skewness or outliers. This analysis will guide your choice of models and evaluation metrics. The next code cell provides a very comprehensive analysis of the target variable. It's designed to automatically identify the last column of the data frame as the target and then generate a variety of visualizations to analyze it. Depending on whether the target is numeric or categorical, the code will produce histograms, box plots, or pie charts to display its distribution, along with summary statistics and information about class balance. This kind of systematic analysis of the target variable is a crucial step in planning your modeling strategy. A fundamental operation in data preparation is selecting and extracting the columns you need. Pandas provides several flexible ways to do this. You can select columns by their name, by their integer position using the iloc accessor, or by their label using the loc accessor. You can also select columns based on their data type, for example, grabbing all numeric columns at once. This is a key step when preparing data for modeling, as you'll always need to separate your features, which we often call X, from your target variable, which we call Y. This next cell provides examples of these different column extraction methods. It shows how to select the first column by its integer position using df.iloc.0. It demonstrates selecting a column by its name, like df_gender, and it shows how to select a slice of columns like the first three using df.lcdf_columns3. The cell also includes code to visualize the extracted columns, for instance, by creating a count plot for a categorical feature or a scatter plot to show the relationship between two numeric features. As we've mentioned, most machine learning models require numerical input. This means that categorical features often need to be converted into a numerical format. A very common technique for this is one-hot encoding. This is especially useful for nominal features where the categories have no inherent order. The following code cell demonstrates how to perform one-hot encoding using the pd_get_dummies function. This powerful function takes your data frame and converts all the categorical columns into new binary columns with a 0 or 1 value. It creates a new column for each unique category. The drop first true argument is an important detail. It's used to avoid a statistical issue called multicollinearity by removing one of the newly created dummy columns for each original feature. For ordinal features, where the categories do have a natural, meaningful order, like low, medium, and high, a simple integer mapping is usually more appropriate than one-hot encoding. This method preserves the ordinal information in the data. This code cell shows exactly how to map an ordinal feature. It first defines a Python dictionary that specifies the mapping from each education level to a corresponding integer. Then, it uses the .map method on the education column to apply this transformation. This is the correct way to handle ordinal data because it retains the inherent order of the categories, which can be valuable information for a machine learning model. Now let's talk about crosstabs and confusion matrices. A crosstab or a crosstabulation is essentially a table that shows the frequency distribution of two or more categorical variables. It's an excellent way to analyze the relationship between them. A confusion matrix is a specific kind of crosstab that is used to evaluate the performance of a classification model. In this cell, we see an example of how to create a crosstab between two columns using the pd crosstab function. The output is a table that shows the frequency count for each combination of categories from the two selected columns. This helps us understand if there's a relationship or pattern between them. Another important concept is feature construction, which is also known as feature engineering. This is the process of creating new, potentially more informative features from the ones that already exist in your data. This can often help to improve the performance of your model by providing it with more meaningful signals. This code cell provides a simple example of feature construction. It creates a new feature called feature sum by simply adding the values of two existing numeric columns. It then visualizes the distribution of this newly created feature. Feature engineering is often a creative process that can have a significant impact on the accuracy of your model. To make these concepts more concrete, we'll now look at two real-world data sets. The first is the vertebrae data set, which is a classic data set used for classification problems. The second is a data set on missed medical appointments, which serves as a great example of an imbalanced data set where one class is much more frequent than the others. First, this code cell loads the vertebrae data set. You'll notice that this file is a bit different. It's space separated and doesn't have a header row. So in the red CSV function, we specify sep9 and header none. This demonstrates the flexibility of Pandas in handling various file formats. Next, this cell loads the dataset on missed medical appointments. After loading, it immediately visualizes the distribution of the no-show target variable. The resulting bar chart clearly shows that the dataset is imbalanced. There are far more patients who showed up for their appointments than those who did not. This is a very common challenge you'll face when working with real-world data. This brings us to a few important definitions. First, unbalanced data, as we just saw, is when the classes in a classification problem are not represented equally. Second, dirty data is a general term for data that has errors, inconsistencies, or missing values. Finally, a term to be aware of is p-hacking. This is a questionable practice of manipulating data or your analysis process just to obtain a statistically significant result, which can lead to false and misleading conclusions. Now, let's move on to our first machine learning model, regression. Regression is a type of supervised learning where the main goal is to predict a continuous outcome variable. The model learns a function that maps the input features to a continuous output value. This cell demonstrates a simple linear regression. The first step is to separate the data into our features x and our numeric target variable y. Then it creates a linear regression model object, trains it on the data using the model fit method, and prints the learned coefficients. Finally, it visualizes the model's performance by creating a scatter plot of the predicted values against the true values. For a good model, these points should lie close to a diagonal line. When we build models, we need to be aware of a few key concepts: generalization, overfitting, and underfitting. Generalization refers to the model's ability to perform well on new, unseen data. Overfitting is what happens when a model learns the training data too well, including the noise, which causes it to perform poorly on new data. Underfitting, on the other hand, is when a model is too simple to capture the underlying patterns in the data, and it performs poorly on both the training and new data. The complexity of a model and the size of the data set are directly related to these concepts. More complex models have the capacity to learn intricate patterns, but they are also more prone to overfitting, especially if the data set is small. The ultimate goal is to find a model with just the right level of complexity for the given data. This is often referred to as the bias variance trade-off. Now let's look at our second algorithm, k-nearest neighbors, or KNN. This is a simple non-parametric algorithm that can be used for regression. For a new data point, it predicts its value by taking the average of the target values of its k-nearest neighbors in the training data. Because KNN relies on calculating distances between data points, it's very important to scale your features before using it. This code cell shows an implementation of KNN for regression. It creates a k-neighbors regressor model setting k to 5. It then fits the model to the data and evaluates its performance using the R-squared score. The cell also includes two helpful visualizations, a scatter plot of the true versus predicted values to visually assess accuracy, and a histogram of the residuals, which are the differences between the true and predicted values, to check for any systematic errors or bias in the model. The KNN algorithm can also be used for classification tasks. In this case, it predicts the class of a new data point by taking a majority vote of the classes of its k nearest neighbors. Just like with KNN regression, feature scaling is crucial, and the choice of k will significantly affect the model's performance. This cell demonstrates KNN for classification. It trains a k-neighbors classifier and evaluates its accuracy. The highlight of this cell is the detailed visualization of the confusion matrix. This matrix is a table that shows how the model's predictions compare to the true labels, giving you a breakdown of correct and incorrect classifications for each class. The visualization here is enhanced to gracefully handle data sets with many classes by only showing every nth label, which keeps the plot readable and professional. A critical part of using the KNN algorithm is choosing the right value for k. Cross-validation is a robust and standard technique for finding this optimal value. It works by splitting the data into multiple parts or folds, and then training and testing the model on different combinations of these folds. This process gives a more reliable estimate of the model's performance for a given k than a single train test split. This final code cell shows how to use cross-validation to find the best k for a KNN regressor. It sets up a loop to test different values of k from 1 to 10. Inside the loop for each value of key, it performs 5-fold cross-validation using the cross-val score function and calculates the mean score across the folds. At the end, it prints out the value of k that resulted in the highest average cross-validation score. This is the standard methodology for tuning hyperparameters like k. To summarize, this lecture has covered the fundamentals of data analysis in Python using the NumPy and Pandas libraries. We've learned how to load, inspect, clean, and transform data. We've explored the key concepts of exploratory data analysis, feature engineering, and the important distinctions between regression and classification. We also implemented 2 fundamental machine learning algorithms, linear regression and k-nearest neighbors, and learned how to evaluate them properly using techniques like cross-validation. These skills form the essential foundation for any data science or machine learning project.